Hello everyone, this is video 13.1. We're going to be looking at polyhedra and other solid shapes. We've not used this word before, so one of the first things we're going to do is actually define the word polyhedra, so make sense of what that even means. Um, yeah, you're going to need a little bit of chapter 12, a little bit of polygons for this. We'll mention that when we get to it. So let's get started. So a polyhedron or polyhedra. This is a Greek etymology word here. So the plural is not going to be polyhedrons, but rather polyhedra. It is a closed, connected shape. Now, what we mean by this is that it should be uh, entirely closed off, right? So think about like a cardboard box that like you open it up, and so now you open those two flaps and you open the other two flaps, and you reach in and you grab the giant teddy bear or whatever you got inside that cardboard box. Now once you do that, you can reach inside the box and take out anything that's inside. There's not a difference between the inside and the outside of the box now. It's all it's all the same thing. That's not what we want. That would be an open box. Now, once I close that box back up, if that giant teddy bear is still inside, then there's a distinction between the teddy bear being inside the box and us being outside the box. Or I don't know, or maybe we're inside the box and the teddy bear is outside. I don't know. But then there's a distinction. So there's a boundary that defines inside versus outside. That's what closed is. Now, the difference between closed and connected um, doesn't seem to make an awful lot of sense to me. So I'm not really sure why Beckman uses both closed and connected, because if it's closed and it's going to be connected, there's not really a way for it to be closed and not connected. Even if we had a side that kind of like if you were to take the cardboard box and put a giant piece of cardboard on top of it, you could say, well, okay, well, it's not connected because the edges of the giant piece aren't hitting the edges of the box, but you can see where they hit. I mean, they still, they don't form explicitly that line, but it's not that big of a deal. So um, I'm not sure exactly why that distinction is made, so I'm not going to worry about it too much. This is in space. So we are making a move from planar objects in space. I'm sorry, planar objects, flat objects in a plane, like squares, rectangles, triangles, trapezoids. They're flat, right? So they're flat objects. Now we're moving into things in space. They're going to have three dimensions. They have length, width, height. They take up volume. They take up space. So this is sort of what's new into chapter 13. We're adding this third dimension in. The last thing is that the outer surfaces have to consist of polygons. And again, if you don't remember what a polygon is, go back and look at chapter 12, or I'll be nice and remind you now. It's going to be a planar shape, a flat shape, where the boundary of that shape is all straight lines. We'll look at a couple of examples here in a moment and see some counterexamples of things that aren't polygons. But we want everything to be, for a polygon, to be straight lines. So I have an example here of a polyhedron. So we see this shape here. Speaking of our cardboard box, this is what a lot of cardboard boxes would look like. It has a more mathematical name, which we'll talk about shortly. But we need to define these three things right here. This is really important. So we've got a face, which is sort of the side of the polyhedron. If you call it a side, everybody will know what you're talking about. But the technical name for this is the face of the polyhedron. And you can see that this face needs to be a polygon. And so you can see, like we said, this rectangle here, we know it's a polygon because it's made up of all straight lines. Faces, so if I've got face 1 and face 2, they'll meet at this line here, and this line we call an edge. Again, if you call it a line, I think everybody would know what you're talking about, but the technical name for this is an edge, so we're going to try to use the right name rather than the wrong name. So these faces will meet here at this line, and really a line segment called an edge. Now, if I take this as face 3, so I got these three faces here, they meet at this corner. And so this corner, this point, we refer to as a vertex. Again, this is another word that has a irregular plural because the plural of vertex is not vertexes, but rather vertices. If you slip up and say vertexes, I'll just make a strange face, but just try to remember it's vertices, not vertexes. Um, Now, likewise, this vertex could be where the three faces meet. It could also be, let's label these edges. Edge A, B, and C also meet at that vertex. Hopefully that makes some degree of sense. If an edge is where two faces meet up and join, then if we've got three faces all meeting, then we also have three edges from where each of the pairs of faces meet up. And so the point where the faces are meeting is also going to be the point where the edges meet. So, I don't know. The book, I only bring this up because the book mentions a vertex as being where several faces meet, but I just wanted to add in it also could be where several edges meet. So these are the main parts in our definition of a polyhedron. So let's look at some special types of polyhedra and look at what makes them what they are and then also how we define them. So the first one we're going to look at is one called a prism. And you've probably seen a prism before, whether you knew it or not. The book mentioned crystal prisms and like light coming through it. So I'm not sure exactly why that was the example that I wanted to use, but sure thing. I guess that works. Um, a prism is characterized by having two polygons, which are called the bases. You can see in these pictures down here, the bases are the little purple sides. And so, we'll focus on, say, this pentagonal prism here. So we can see we've got these two pentagons. There you go. And so you can also see that the name of the prism is based on the base shape. So if these have pentagons as bases, it's a pentagonal or pentagonal prism, however you want to say it. This has triangles as bases, so it's a triangular prism. This has rectangles as bases, rectangular prism. And so we've got these two base shapes, and they need to be um, congruent. They need to be the same shape, and they also need to be parallel. And so they're going to make this sort of like nice, pair of flat objects. And then we just connect using edges these corresponding vertices. And so the one that's at 12 o'clock here connects to 12 o'clock here, 10 o'clock to 10 o'clock, 2 o'clock to 2 o'clock, so on and so on. So we've got these two shapes, and if you draw one, here we'll draw. So when you draw a prism, you get a pretty clear idea of what's going on. So you draw these two rectangles and then connect here to there, here to there. There you go. So there's our rectangular prism. I do want to point out that if you were to take this rectangular prism right here and flip it over on its side, then the top and bottom would also be rectangles, and this would still work as a rectangular prism. So these two sides here, the ones on the side, these two faces on the side, I should say, could still work as bases. Although if I were to take this pentagonal prism and flip it over on its side, if I try to make this a base, then I don't have another base on the other side. And even if I did, because the pentagons are on the side, they're not connecting the way I want. Now, I'm being pretty restrictive here because realistically, the bases don't have to be the top and the bottom. They could be the sides, they could be the front and the back, they could be whatever. But I'm just talking about the bases being the top and the bottom to be consistent with what we're seeing on the slide. So the bases don't necessarily have to be the top and bottom. They just have to be the two congruent sides that connect. This rectangular prism has a couple different choices because everything that is formed is a rectangle. The lateral faces, as they're called, the faces on the sides of the polyhedron, because they're all rectangles, any of them could work as bases. For a pentagonal prism, the bases have to be pentagons. There's only one pair of pentagons, so none of the lateral faces would work as bases. All right, I've said way too much about prisms. Sorry about that. Okay, so another distinction that we need to make with prisms is between a right prism and an oblique prism. And for the most part, you'll know it when you see it. A right prism's got nice right angles in there. So you can see there's a right angle here between this lateral face and this base. And so really it's not that right angle that we're looking at, it's that right angle. So you can see here, this would be a base. Well, no, this would work too because it's still to the base. Yeah. So these are all right angles that show this is a right prism. You'll know because it's standing straight up. It looks like a right angle. I mean, it looks square, which is kind of what we want. For an oblique prism, we can see it's also easy to tell because it's leaning. There you go. This angle here between the lateral face and the base is not a right angle. So this is not a right angle. Now, don't get confused with this. This is the one that is a little confusing. So there's a right angle here. This right angle is only within the base. It's just the angle of one edge of the base to another edge of the base. Realistically, if we look over here, this would still be a right angle here because this base shape is still a rectangle. So this contains a right angle, but it's not a right prism because the right angle needs to be between a lateral face and a base. And this is not. This is just within the base. So, I don't know, a little sneaky, a little tricky, not overly so, but you do need to pay attention to what the angle is between. And again, we want it to be, for a right prism, we want the right angle to be between a lateral face and the base face. All right, so similar to a prism is a cylinder. Now, in a cylinder, the base shape is a circle typically, although your book points out that it could at least be something circular in nature, like an oval. I'm not sure that I've ever really considered an oval to form a cylinder. I always think of it as being a circle, but I mean, no reason why it couldn't work. And there's some examples later on in the book that are kind of like round, curvy, that look like a kidney bean almost, base shape, and they call that a cylinder also. I guess that's somewhat circular in nature. I think by circular, the book's just trying to say curvy, but I guess if we agree that it works, I guess it works. Anyway, the point is that this circle, this oval, this kidney bean, whatever curvy shape we're using, they're not polygons. Because remember, a polygon has to have straight edges defining its boundary. And once it starts being curvy like this, then it's not a polygon. And if it's not a polygon for a base shape, then it's not a polyhedron. So we're not saying that cylinders are, less valid as shapes, or that we're not going to talk about them, because clearly we're talking about them. In the same way that we're not going to dismiss circles just because they're not polygons. We just need to recognize that certain characteristics now are not going to apply based on the fact that they are curvy and not polygons or polyhedrons. So they're still solids. They're still spatial shapes. They're still three-dimensional shapes in space. But cylinders just aren't polyhedra. Yeah, it happens. We also have a right circular cylinder. We can see here, this is a right, and then this oblique. Now, again, the right, we're going to measure based on this height, and this height goes from the center of this circle to the center of this circle. Realistically now, we got a little bit of a problem, because if we take the book's definition and it's an oval, we might have a harder time finding that center, because we haven't really talked about that. If it's a kidney bean, I don't know how to find the center of a kidney bean. I don't even know what that looks like. So we could just take any corresponding point to any other corresponding point. It doesn't have to necessarily be the center. And we want to look at that edge, and then if it's at a right angle to the base, then it's a right cylinder. If we take corresponding point to corresponding point, connect those, and then look at that angle, that's not a right angle. So now we know, and if we do the same thing over here, we get a different angle. We get the obtuse angle on this side. Then we can tell it's not right, so it's oblique. So if there's any corresponding point whose edge is not at a right angle to the base, then we know that it's not a right cylinder, and therefore an oblique cylinder. All right, so similar to prisms is the idea of a pyramid. And for a pyramid, we've got just one of the bases of the prism has been replaced with a single point, which we call the apex. So if you go back and look, we had a triangular prism before. So there was a triangle up here and they all connected. But instead of the three parts of the triangle connecting to the corresponding 3 points, they just connect that one single point. Here we've got a square or rectangular base that's connecting up to this apex. And here we've got our pentagonal base, which also connects up to this apex. Again, we're going to define what type of pyramid it is by the base shape: triangular pyramid, rectangular pyramid, pentagonal pyramid, same thing. And we also have right and oblique pyramids. It is a little bit harder to see what's going on here. Our base shape has to have some sort of center, and this is going to work out a little bit easier if we're looking at rectangles and squares, because it's just going to be the intersection of these diameters, or I'm sorry, diagonals. So it's just about where you might expect it to be. We can find a center for a triangle, but it's not anything that we've talked about and nothing that we're going to talk about in this class. We could also find a center of a pentagon, hexagon, especially irregular pentagons, hexagons, octagons, whatever. Again, not something we're going to cover in this class. So just assume that every shape has a center, although we may not be talking about how to find it in this class. But for a rectangle, you can find it, and it's where you would intuitively probably expect it to be. So if you look at the apex and drop it straight down, if it hits the center of the shape, like over here to the right, this drops straight down to the center. This lets us know that the apex is directly over the center, so it's nice and symmetrical and balanced. That would be a right pyramid. If the apex is off to the side of the center, then it has this kind of lean to it, and so that's what makes it oblique. We can't do it based on the lateral faces because they're all going to be leaning in. And so the lateral faces are not going to be at right angles. So we can't use the same criteria that we used for prisms. We have to use a different criterion, dropping that apex, dropping it on an edge from the apex down to the base and seeing where it hits. So in the same way that we had prisms and then cylinders, we also have pyramids and then cones. The book gave a nice definition that a cone is like an ice cream cone. That's maybe the worst piece of mathematics I've seen in this entire book. Because, I mean, number one, there's a lot of ice cream cones that are not cones. There's the ones like the little flat bottoms that have like the two kind of like tiers to it. So really, what the book's talking about is a sugar cone. But a sugar cone also doesn't really work because a sugar cone isn't closed. I mean, the whole point of a sugar cone is that you can put ice cream in the cone. If an ice cream cone was like a cone, there would be a thing at the top, and when you put ice cream on it, it would hit the top, and it wouldn't work. I mean, it would be a horrible example. Anyway, I don't know why I just don't say that it's a pyramid with a circle as base, or it's like a pyramid except it has a circle as a base. So yeah, the ice cream cone thing kind of stinks. So anyway, so it's a base shape of a circle or circular type object. So again, the book has expanded this out to being any kind of curvy object as the base. And again, all of those the points along the edge of the circular object, the circle or oval or the kidney bean, whatever it is, they all go up to that top point called the apex again. I don't know why this graphic that I found online just says vertices, because really it should be vertex because we're looking at just each one individually, and then these are still an apex. So we're still talking about these going up to this apex. Anyway, so yeah, this is a cone. Again, just like with a pyramid, we can see if it's right based on if the apex is over the center or not. If it is, it's a right cone. If it is not directly over the center, if you drop it straight down, you can see that it's not over the center, so then that makes this an oblique cone. All right. The last topic is sort of an optional topic, but I thought it was interesting, so I wanted to throw it in there. We've got these 5 kind of special solids that are called the platonic solids. because they were used and discussed by the ancient philosopher Plato quite a bit. Sometimes you'll see them just called the regular solids. I guess people who have a problem with Plato, for whatever reason, they call them a regular solid. And well, regular solid means that all of the faces are going to be the same type of polygon. So we talked before about a regular polygon. We said that a regular polygon was one where all the side lengths and all the angles were the same, or the same measure at least. All the sides were the same length, all the angles were the same measure, and that made it a regular polygon. So a regular polyhedron, all the things that define its boundary, in this case the polygons, need to be the exact same polygon. And so you can see here for this first one, this cube, which doesn't look very cubish, it looks like rectangles, but whatever. It needs to be a cube because all the faces need to be exactly the same. You can see that it's made up of 6 squares, and that makes this cube. This triangular pyramid here is made up of 4 triangles, 4 equilateral triangles specifically. We've got our dodecagon here, so there's 12 sides, and they're all made up of these regular pentagons. We've also got, next to that, the big one, the 20-sided one, that's our icosahedron. And these names are all in the book, so if you have any questions about the names. And I think they appear on a later slide, or in a later section. So this is my, I might as well just go ahead and write it. So this is my dodecahedron, and this is a icosahedron. That's an A. And then this is just an octahedron. This is a cube. I should have to write this down, but I'm going to anyway. And this is a triangular pyramid. Anyway, so you can see that here for this octahedron, it's made up of this equilateral triangle, and there's 8 of them that join together. So these are the only 5 cases. These are the only 5 cases, the only 5 solids that we can form using the same polygon. And so they're kind of special that way. If you look in the book, they talk about some alchemy purposes that Plato had for them, and this represents fire, and this represents earth, and this represents roast beef or something. So that's not really that important. We're not going to talk about that too much. But if you find this sort of interesting, there's a lot to it. So certainly look into it. The real reason why I wanted to bring up the Platonic solids, they're sort of interesting, but to get to this. Now, if you take those Platonic solids and you start to cut off at the corners, if you start to cut at the vertices of those polyhedra, then you start to get other shapes. And so you can see here this truncated tetrahedron. And so this would be that pyramid, the triangular pyramid. If you start to cut it at the vertices, then you form this shape. And so then the same thing with the octahedron, and then here, this may be a little bit easier one to see, this cube. If I were to take that cube, let me draw this, and you'll see what I'm talking about. So I would take this cube, and then I'm going to cut it at this corner. And so if I cut this corner off right here, so then that's gone. And so what's left here is this little triangle where I've cut it. Now, if I do that at all of the corners, then this, what used to be a square here on the side of this cube, has now become an octagon, and there's a little triangle here. And so these are the semi-regular or Archimedean solids, and these are made up of exactly 2 polygons. Or 2 different types of polygons. Some of these are made up of more of this great rhombocubotetrahedron is made up of more than that. But this was the whole point right here. The truncated icosahedron. Because it's a soccer ball. There you go. That was the whole point. I thought that was interesting. So now the next time you see a soccer ball, you can call it a truncated icosahedron. Or don't. So if you're a checkpoint problem, I want you to either draw, which would be good practice, but if you're not comfortable with your drawing, I understand. Or find pictures of a couple different prisms. I would say probably 3 or 4 different prisms, and then make like a little chart with the base shape of that prism, and then count the total number of edges in that prism, and also count the total number of vertices in that prism. Do you see a pattern? Do you see a connection between the base shape and the number of edges or the number of vertices? We will talk about whether or not there is a pattern, and if there is a pattern, what that pattern is in class. Also, try the same thing with a pyramid. Do you see any sort of pattern between the base shape of a pyramid with its number of edges and its number of vertices? So if you have any questions about this problem or anything else from this section, as always, please bring your questions to class. All right, thanks.